Hello, everyone. I'm Sejin Kim, and I'm from the AI Center at KIAS. It is an honor to present my talk titled AI-based solution to immersive problem in holography. I would like to thank the organizers for inviting me and giving me this opportunity. I will begin by reviewing the basic of gauge-gravity duality and the inverse problem in holography. Then I will introduce the generative AI and explain its significance. After that, I will describe how we apply the AI model to study entanglement entropy and superconductor in holography. Finally, I will conclude with our result and future directions. Holography principle has long and rich histories. Wittgenstein and Hawking discovered that black hole entropy is proportional to the area of event horizon, suggesting that information is stored in a two-dimensional surface rather than three-dimensional volume. In 1993, Tupft formulated the holographic principle more precisely, and Maldacena introduced the ADS-CF correspondence, which relates the gravity in ADS space to confirm field theory on the boundary. Since 2010, computation tool, including machine learning, has become increasingly important in holographic theory. The ADS-CF correspondence provide a mapping between the bulk gravity and boundary field theory. Local operators in ADS space correspond local in boundary component field theory corresponding to bulk field in ADS space. For example, local operator O on the boundary is mapped to a scalar field phi in the bulk, where the radial coordinate set include the energy scale in the CFT. The temperature of a black hole is corresponding to temperature of thermal state in boundary theory. This dictionary forms the basis of our research. The strongly correlated systems are characterized by interaction between the particles that are stronger than their kinetic energy. In such systems, standard method often fail. These systems exhibit unconventional and rich phenomena such as high temperature superconductor, heavy fermion material, quantum critical point, and Fock-Gluon plasma. Their strong coupling and emergent effect make them difficult to analyze using conventional numerical and analytical techniques. Holography principle provide a powerful framework for this, for investigate these complex systems. It enables us to model superconductivity using charged black hole and complex scalar, describe key features of Fock-Gluon plasma, and gain insight into non-ferromagnetic liquid behavior. For the problem in holography is well understood. We calculate the boundary quantities from the given bulk geometry. For example, we solve differential equation of motion for bulk field with appropriate black hole horizon conditions, often using shooting method, and then extract physical quantities from at the boundary. This direction is a code problem. In contrast, the inverse problem is much more challenging, reconstructing geometry or holographic theory from the boundary data. There is no known analytical solutions. Traditionally, this requires searching over many parameters and relying on numerical trial and error. This motivate our use of artificial intelligence for more stable and efficient solutions. The generative AI for holography offers several advantages for addressing inverse problem in holography. First, a neural net can uncover the hidden patterns and complex correlations in high-dimensional vector data. And second, holography allows us to verify whether the prediction made by AI are correct or not. And third, a trained AI model can immediately predict dual geometry or holography theory from boundary physical quantities. Finally, a well-trained AI model may suggest a novel theoretical structure or unexpected result. The transform model is a neural network architecture widely used in natural language processing and scientific computing. This is most famous figure represent attention-oriented paper written by Google. Here, encoder and decoder are each made up of multiple layers, looks like this. And the data keeps the same shape as moves through them. This makes it possible to build deep and complex and powerful models. Each layers comprise multi-head attention layer and feed-forward network. Attention compute correlations among all positions of the input, while multi-head attention enable several attention mechanisms to operate in parallel. Each is capturing distinct features and patterns in the data. Here, residual connection and normalization help preserve information and stable learning. The feed-forward network extracts nonlinear features at each position of the input. The positional encoding layer is added to encode the order of input elements. So the attention-based AI model allows for fast, scalable, and parallel processing, making transform model highly effective for a range of machine learning tasks. So in our work, first we boundary quantities convert into sequence. Then each sequence element is mapped to high-dimensional vector through input embedding dimension. And multi-head attention extract complex patterns from this embedded in sequence. And encoders feed-forward network process these representations and output latent tensor, which then decoders use to sequentially generate each bulk quantities at one at a time. Attention mechanisms act like an effective interaction matrix, dynamically assigning coupling strength between the element of the input and output. It is similar to how Hamiltonian describe interaction in a physical systems. It enables the model to capture non-local relationship, much like a green function reveal one part of a system, how one part of system influence other. So the attention mechanism is computed using matrix multiplications and softmax functions. Attention compare all part of the input via query, key, and value, weighting more important connections more highly. This allows the model to focus on key information and understanding global patterns, which is particularly important in holography. In particular, attention mechanism can uncover the relationship between the boundary data and bulk data. So, yes. Yeah, let's go to physics. Yeah, the new top. Yeah. Yes. I thought. Uh-huh. If we, uh, this is about boundary data. This is bulk data. If feed the term data into the model, then the attention had attention calculate some connections and correlations between the input and output. Then the model gives some next bulk quantity.
You also said attention layer is like a Hamiltonian. What
Yes.
do you mean by that?
Ah. Okay. Attention. I will show you later. Yes. I will show you attention map. This is easy to explain what it means. The new Takai formula connects the entanglement entropy to the area of minimal surface in the bulk. In the figure, the center circle represents the black hole and outer circle the boundary. Here, rho A, rho B are the quantum reduced density matrix for region A and B representatively. In quantum field theory, the entanglement entropy is computed by partitioning the system to region and tracing out the degree of freedom in region B to obtain the reduced density matrix rho A. Then the von Neumann entropy of rho A is the entanglement entropy between region A and B. In holographic context, dividing the boundary into two regions, and the entanglement entropy is proportional to the area of minimal surface gamma A. To compute the entanglement entropy for strip-shaped boundary in T plus 1 ADS black hole, we begin with the specific battery adjustment like this. Z equals 0 is the boundary, and large L is the ADS radius. And here small l is width of region A. We apply the new Takai formula to evaluate the entanglement entropy, which can be interpreted as an action like this with x1. It is playing role over time. The translation symmetry in this context implies that Hamiltonian is conserved. So translation symmetry leads to a conserved Hamiltonian. The turning point ZT is where the ZT x1 vanish. As the turning point approach black hole horizon ZH, the Hamiltonian approach 1 over ZH to B minus per 1 power. It is some constant. And Hamilton-Jacobi equation tells us that the derivative of the entanglement entropy with respect to the boundary size L is minus the Hamiltonian. For large L limit, the entanglement entropy grows linearly with L. If SL is given, we can estimate the black hole horizon from the larger limit. Okay. Using Hamilton-Jacobi equation, this equation, L and ZT can be expressed in terms of each other. So we can reconstruct the LZT on the left side, and the Hamiltonian constraint to provide the integral formula on the right side here. This is a basic basis of our work. In the fourth problem, we can compute the entanglement entropy using an explicit integral formula like this. However, this equation is not invertible, so there is no known method to recover F from the entanglement entropy directly. This fourth problem is this way. In contrast, the inverse problem is much more challenging to reconstruct the bulk matrix. We therefore train an AI model to recover the inverse mapping this way. We calculate S prime and construct the LZT as input to the model, which then predict F for dual geometry. Our transform model also operate as sequence-to-sequence model. So where we convert L and F into a sequence where Li depends only on F1 through Fi to calculate. Importantly, the Fi plus 1 is not necessary for calculating Li. When solving inverse problem, if F1 to Fi is given, the value of Fi plus 1 can be determined by Li plus 1. As a result, the attention map for this task is diagonal, reflecting direct correspondence between the element of input and output data. Okay. Yeah.
Is H
Yeah.
holographic entanglement entropy?
Yeah. H?
What is the definition of H?
H is Hamiltonian or
Hamiltonian.
from.
So
we consider this some action there is some translation symmetry or time translation symmetry. We can define the Hamiltonian as constant, some constant.
So 이거가 이제 derivative of holograph. I see. So excuse me.
Here, this figure shows the randomly generated geometry. The Black-Knight factor F is conducted by adding standard black hole solution plus some white noise. For each sample's input is LZT and output is FZ. We create 0.1 billion examples using new Takai formula numerically for randomly generated geometry. Here, it is correspondent to the entanglement entropy by LZT. Our transform model comprises 3 encoder, 3 decoder with A-head multi-attention and embedding dimension is 5 tail. And the model was trained with the Adam optimization for 2004, batch size of 512, and dropout regularization to prevent overfitting. Unlike natural language task, where the relationship between the word can be ambiguous. Here, the correlations between the input and output are governed by a an explicit physical law from holography. This makes the inverse problems more straightforward for transformer model to run. Our model achieve 99.3% accuracy in three-dimensional model and 96.1% in four-dimensional model. And the mean scale error is less than 10 to the minus 5. In the tension map, the diagonal structure is visible in both cases. This is three-dimensional and four-dimensional, which means if metric sequence element, there is a very high value. It means this sequence element highly correlated with this given entanglement data.
How did you compute the accuracy? Can you explain?
Accuracy.
So what is the
validation data? We compute. We test the validated data and compare the true data.
true data is what? How do you get the true data?
True data is very simple because we use a Utah formula. So this is a true data. I mean, we use this noise black hole geometry to compute the entanglement entropy. Then this pair is true data. True data, yes, from this. This is true from yes. Yes, the specific form is the standard black hole solution plus white noise. Yes, this is if we consider three-dimensional, then this is it is black hole case. Then D is 2. Then the black hole factor like this. On my scale.
That input was then encoded with
What is in?
That's the
Encoder, decoder. Encoder, decoder. Transform model has encoder, decoder structure. If we input some data, yes, it's very famous figure. So these figures shows our result for geometry outside training set. Tom rows shows the result for three-dimensional model, and bottom row shows the four-dimensional model. Even if we the AI model was trained only on noised black hole geometry, but it accurately predict these smooth case. The three-dimensional model, from left to right, the examples are 1 minus Z, 1 minus square, 1 minus cube, and charged black hole case for each dimension.
So I do that. So the AI model is just denoising it. So you have a gravity solution. You add artificial noise onto it.
Yeah.
And then the machine learning model denoises it and gets the original gravity model back, or is that what is happening?
The model also predicts smooth case.
Smooth case?
Yes.
You mean without noise?
Yeah, or without noise. Yeah, it is outside of training set, which means there is a noise. Training set is comprised and consists of a noise black hole solution case. Yeah.
So the black hole solution is already known. You just add noise.
Yeah.
And then the machine learning tries to reconstruct the original black hole.
Yes. Additionally, we trained this is a standard black hole solution in 3 dimensions, but it can also predict different power here, and charge black hole case too. Yes. 4-dimensional model is standard black hole solution is here, we also can predict these cases. 3D model perform almost perfectly for 4 cases, while 4-dimensional model is less accurate at the boundary here, two boundaries, especially the charged black case. If the model makes some error at the start, it tends to adjoint the later value, causing discontinuity. Yes, Q is charged for 4-dimensional model. Oh, very the 1.7 is almost an extreme prequel. Yes, because there is the derivative of Blackman factor almost 0. Here, this is a black hole position. Yes. So I will briefly show you how AI model work. Here, first I import the trained 3D model from Python into Mathematica. I will begin with a demonstration with BTG black hole case. For BTG black hole, the entanglement entropy has explicit formula that is computed in the form of log of sine hyperbolic function. 이렇게 here. ZH is black hole and epsilon is UV cutoff. Okay. As I mentioned earlier, we can estimate the black hole horizon from the large limit. We can find the black hole horizon. We can find here. Using Hamilton-Jacobi-equation, we set this factor 1/2g to 1. So Hamilton-Jacobi-equation is very simple. And using Hamilton-Jacobi-equation, we construct LZT and convert into sequence. This is the input sequence. Okay. Then we set the first output is 1. This is because the boundary is UV limit, so we method factor should be 1 for ADS, ultimately ADS limit. Feeding n-type L sequence together with the initial output into the model provide the next output value. We take which tend to output list. Output list. Iterating this process. Okay, this figure, blue curve is black hole solution, and while the red curve shows how AI sequentially generate the blackening factor from boundary to horizon. I will show you one more time. Here, sequence generated like it's working like ChatGPT. Very close. Next, let's consider the case where the entanglement entropy is given as not given not as a function but discrete data. I create the entanglement entropy data as a function of L, like this, LS, using the charged black hole, charged BTG black hole with horizon size 10. Okay. First, we interpolate the given data, and then we determine the black horizon from larger limit. Using Hamilton-Jacobi equation, we reconstruct LZ and convert. The model is scaled by black horizon, so we first find the black horizon size and compute the rescaled L sequence. This is the L sequence. Then, okay, supplying the L sequence and input and initial output with of one to generate sequentially generate recurring factor that I use give the entanglement entropy data like this. It is work. This case also work. As next, finally, as on aside, let us test the model in non-black hole case. This entanglement entropy is the time-like entanglement entropy of BTG black hole. So it is given in the form of log of sine function. We can confirm that this is not black hole geometry from large limit. Although it is not black hole case, the Hamilton-Jacobi equation still hold. So we can compute the L sequence like this, and the output is this model provide an unusual form of F. It's not black hole case. To verify that the result is correct, we compute the LZT from the F and compare it with the input LZT. Then we can confirm that this is a solution to our input data. This is true solution. So connection to ADS. Yeah, yes, UV is always ADS. IR is, I'm not sure. There's some. Oh, I don't know. Hey, let me say.
From BGC. I think the form is from pure ADS.
Pure ADS.
I mean, if you consider the entanglement entropy of black hole, the sign part
Yes.
may be hypothesis based on time.
This is time-like entanglement entropy of BTG, right? Yes. This topic is different. Yes.
So where is the temperature?
Temperature, low horizon, we can confirm that this is not black hole from the large limit. There is not the entanglement entropy not grows linearly for large limit. Yeah. So we can understand. We understand it is not black hole. This overcome arise because the transformer model have correctly learned the effect of the weight function in this equation. So it is possible to predict the non-black hole cases. So let me turn to holographic superconductor. In our setup, 4-dimensional ADS black hole is coupled to Yuan gauge field and charge bulk case. Superconducting phase appears as hairy black hole solution, and conductivity looks like that of a real superconductor. Over the past year, we extended this framework by adding complex interaction terms like this, which allow us to generate a range of superconducting phase diagram. The phase boundary separates the superconducting state from normal metal. It and corresponds to transition from charged black hole to hairy one. Along the phase boundary, scalar field contribution is weak, while high order effect become important inside the superconducting state. Even if we consider a very general theory, the phase boundary lies in a region where scalar field effect is weak. So this description is general enough to study the phase boundary. In the probe limit, we solve scalar field equation on the Reisner-Rostrom black hole background. And this is metric ansatz, and this is a gauge field ansatz. And this equation shows the background solutions. Here, chi is a real scalar field responsible for momentum relaxation. The temperature is proportional to the derivative of black length vector at the black hole horizon. Near boundary, scalar field exhibit on its specific asymptotic behavior, where delta plus or minus are conformal dimension of the operator. Here, J and O source and expectation value of the operator, respectively. Superconducting state arise when J vanish. So by choosing Q and kappa at the black hole horizon and using shooting method to find where J vanish, we obtain the phase boundary. In the figure shows our result. The yellow lines correspond to M function, and blue curves are the phase boundary from the holography. The shape of the M function and the phase boundary closely matching. Yes, you can see.
Yeah, so it's yellow one is
M function. F square is 0. Q equals 0 because F is square.
Tell me again about the meaning of yellow curve when
Yellow curve is M function.
M?
M, yes, is this M function. If we give M function, then the base boundary is
And
fixed.
it's a function.
Yes, highly non-trivial function.
Then what was the operation?
Q over kappa square.
But you said that's the function of F squared.
Yes, but at the black hole horizon, the F scale is equal to -2 Q scale. So
But that F is not function, it's the number.
yes,
But yeah, you can write
yes. So we can plot together. For the problem, given M, color field satisfy an explicit equation by setting Q and kappa at the black horizon and using shooting method, we determined where J vanish through the obtaining the phase boundary. This way.
So if the Q is the charge, right?
Yes, charge. Kappa is the real color field solution. Kappa is momentum relaxation.
Momentum relaxation.
Yes.
Right.
Yes. This way. So in the inverse problem, the both axes here and here, P and X axis are function of Q and kappa. So the phase boundary can be expressed as kappa Q if the phase boundary is given. By providing the AM model with the relationship between M and kappa Q, it learned to recover M function from a given kappa Q through solving inverse problem. And I can solve this.
I still don't understand the meaning of M as a function of X squared. Can I look at your action?
Yeah.
So that means, for example, that M then over X squared, so that simply can be X squared. Right?
Yes.
And
But yeah.
I'm talking by so then action is changing or what?
Action is changing.
So in your action, the standard Maxwell action is
Yeah.
X squared. Can I take your action? Yes. So for example, the Maxwell action is fixed as a X squared.
Yeah.
Right. Then that can be any function of X squared.
Yes. Any function.
So then your machine is now
predicting, yes.
suggesting some very complicated
function, yeah.
as a company.
Yes, yes. Yes. To utilize transform model, we convert M and kappa into sequence. To compute the kappa I, only M1 to MI need. The MI plus 1 is not required for kappa, calculating kappa I. When solving inverse problem, if M1 to MI are given, then the MI plus 1 can be determined by kappa I plus. As a result, the tension map diagonal as before. Okay. We create a training set by generating M function as constant plus some white noise. For each M, we calculate kappa Q using holography theory. You can see the kappa Q is highly sensitive to M function. The kappa Q serve as input and M as output. Our model comprises 3 encoder, 3 decoder with a head multi-attention and embedding dimension is 510. The model was trained with Adam optimization for 2000 epoch and patch size 1/128 and dropout regularization to prevent overfitting. Our trained AM model achieved 97.8% accuracy with the mean scale error of 10 to the minus 5. The tension map is diagonal. Diagonal structure is visible clearly here. This smooth case was randomly generated and feed to the model. Using holography theory, we reconstruct the phase boundary from the predict M function and compare it with the input sequence, input phase boundary to directly quantify accuracy. Double valued function 차지 double valued
Even true,
이-
there are three
phase transition. Yes, this is phase boundary.
The right side of the figure.
Yeah, right side of figure. You mean this is I'm not I don't know, but it is possible to construct this phase boundary from holography theory. I generate M function arbitrarily and compute the phase boundary, then we obtain this old phase boundary.
Yeah, I think it's possible. Maybe there's a way it should be here.
Twice. Yeah. Yeah. So because you can see the phase boundary is highly sensitive to M function. The performance here is slightly below the entanglement entropy task. However, the further optimization should improve the result. Let me conclude. We apply a simple transform model to solve inverse problem, both in geometry and theory reconstruction. This approach is accurate, efficient, and interpretable. In the future, we plan to scale up our model to reconstruct second-order differentiation from the boundary data, apply our model to experimental condensed matter systems, and explore further transfer learning in other holographic contexts. I introduced our research related with the inverse problem. I hope this section would be helpful for you. Thank you for attention.